What's happening, internet? Good evening time to you guys. So the reason we're all gathered here today is we're going to look at a Worthmore 600. In my Facebook group, I had a gentleman ask a question about Worthmore amplifiers, and he goes, I can't find any information on them anywhere. And of course, what all the guys did was very quickly throw up videos that I have made on this particular style of amp. Worthmore was a neat dude, and he was completely run out of business. The safety police come down on him like a ton of bricks. This is a neat amp, completely hand-built, literally built in somebody's garage, with the power of a Dremel and straight-up motivation, which I admire. I can admire that. We'll disconnect the band board. Come on. Come on, Mr. BNC. All right. So this is a Worthmore 4-pill. This is a Worthmore 600. They basically all have the exact same layout internally. This one is basically virgin. We've got our input attenuator circuit. This is what keeps us from overdriving the amplifier, and it hides the input tune, because the palette is set up to have a flat response across 0 through 30 megahertz, right? This is our output network, and we can see that our output resistor's slightly discolored over here. We set this up also as a very flat response, the output network. Now over here on the band board, which is all cut by hand, actually this must have been a later model because this is etched. This isn't Dremel cut. I've seen these where these are all completely Dremel cut. The blueprints for making this filter board are basically everywhere. They're all exactly the same. They're just a very simple trap that will either let frequencies below, well, they all work the same. This will cut everything above 10 meters. Then this cuts everything below 15 and 20 and all the way down to 160. So it's a notch filter that will let everything above in frequency, but below it, it'll let it go through. Everything above in frequency, it cuts it out. This amplifier is here because this gentleman was keying this amp and using it and talking on it and operating it and having a good time with it, and then it just stopped talking. And I said, well, doesn't it have an auxiliary jack? And he goes, no, there's no jack on the back of this at all. Most of Worthmore's boxes had this RCA that was attached on the back. We're going to add this one today, and we're going to put a switch on it. So we're going to have the switch in one position be the auto key, which is great for AM, not so hot for CW, and not so hot for sideband. So he'll be able to switch the auto key out and put the manual key in. Now, I can almost bet money, if I was a betting man, right down here is the key-in transistor. This is a 2N222 key-in transistor, the most common transistor man's ever created. Arguably would be one of the most common transistors man's ever created. They're a little bit delicate to fast pulses of energy, hence the reason why we put this little tiny filter cap here across the legs of the transistor. But they're notorious for giving up the ghost. So our next step up in transistor is to go completely balls over the top with it. And then we'll use something like a tip 31. They look a lot like this. Here is the Mauser part number if you're interested. This is a tip 55. It's basically the equivalent to the tip 31 today. So the 3055, that's the actual part number. This is way overkill. This will work fine, but I can tell you right now that all we got to do is go in and replace this literally 2-cent part. If you buy it in bulk, anything over 100 parts, you're only paying about 1 cent to maybe 2 cents for that transistor. RF's coming in, it's not exciting the transistor no more, and the relays aren't closing, so there's no power being made. So then when I meet up with the guy, he explains to me that he does not, on the back of his ICOM 706 Mark II G, he does not have an auxiliary out. And I said, no, they all do. And he goes, what do you mean? I said, man, you're gonna have to get on Amazon. We're gonna insert a picture here of the auxiliary to amplifier key function. It's a DIN plug that goes to an RCA out. And what that actually does is it gives us a 12 volt ground signal from that plug. So what we're going to do is we're going to go and we're going to bypass. We'll jumper in. There's a little jumper that's right here. There's a little jumper that's right here. We're going to remove that jumper. Then on the back wall, probably somewhere back in here, we're going to mount up our switch so that in one position he's got manual key, and then in another position he's got automatic key. Then right next to it we're going to hook up this RCA jack, this Princess or fancy RCA jack. And what that'll allow it to do is it'll give it a ground signal from the radio. So when he keys the mic on his radio, which is primarily sideband on his ICOM 706 Mark II, not Mark IIG, but Mark II, it'll manually force the relays to shut, but it'll hold the relays shut, and it's not reliant on RF coming from the radio to energize the circuit, and it'll protect the relay contacts. You gotta think of them like points in a car, and every time you modulate, they're drawing a little bit of an arc, either it be from the RF coming in or the RF going out on the other side of the relay. In this case, RF coming in, RF going out. It's going to draw a little bit of an arc every single time. Well, that's an accumulative effect, and eventually you start to lose receive because the relay contact points start to get burned up. Excuse me one second. Sorry, I had a little frog in my throat there. Essentially what this does is it keeps the relays latched when it's in the manual operation. So it gets it a ground. The radio itself can only put out like 1/4 of an amp. It's actually a MOSFET. They don't use a relay inside anymore. It's a MOSFET driven send signal. So you don't want to use that directly to run, let's say, your 110 volt ground. Technically it is giving it ground, but there's not enough current there, and it's the wrong kind of current handling capability for us to key most of our old-time boat anchors that run with 110 volt relays and that kind of thing. So that's why MFJ made that intermediate box that sits between the radio and the amplifier, but we don't need that here. This is more than the relays here will not pull anything more than what the radio can't handle put out. Now I was initially thinking I would put one of these big badass transistors in here, but that's super overkill, and I got to modify the circuit quite a bit. I mean, I even made up all the sub parts to make this happen. Got to use some, little glass diodes, and got myself a different sensor cap and all that kind of crap. We're not going to do any of that. I'm going to go in here, I'm going to replace the 2N222 transistor. We're going to get it so it operates again, and then we're going to add that manual key function, because I guarantee you this thing's going to spend the rest of its life. I've met this guy, I know this guy, I know the kind of person he is. Like I've gauged that out, right, to what kind of person he is. And he is the kind of person that's going to get that manual key jumper off of Amazon for like $15 or $20 or whatever it is, and that's what's going to make this thing transmit. So we don't need to add the overkill part, because I know the kind of customer. And that's, you guys, this is not an 11 meter amplifier. It will work on 11 meters, but it's not going to work as well. A 4-pill for me does, depending on what kind of drive you put in it, anywhere from 400 watts all the way up to 1200 watts, depending on the drive. This thing here, you'll be lucky if you get 600 out of it in the 11 meter band. That's why we see so many of these butchered and modified to work on the CB frequency, because CBers buy them thinking, oh, it's just an amp, and then it doesn't work the same. And it's because the board, the actual pallet, is not designed to operate on 11 meters. It's designed to operate on everything. And how we get such more performance out of the transistors is that we have narrowed its frequency of operation. We make it very narrow, and when we do that, we can hyper tune the circuit to the transistor and radically increase the efficiency of the circuit, so therefore we can get a higher sensitivity and more response out of the transistor. Where this here, it's a flat response over a large bandwidth, and we use the filter board to cut out all the harmonics, and then we use our input to hide the out of resonance input of the pallet. I get the comment all the time, you know, CB amplifiers are splatter boxes. Well, I haven't seen that to be the case. I haven't. I've seen amateur solid state boxes produce way more harmonics than a specifically tuned monoband CB amplifier. It's the nature of the beast, you guys. You can't argue against the logic. Wide response versus mono frequency response to amplifier. That's why there's no filter networks on most CB amps, because if you try to use them at any other place than 11 meters, they're not going to work right. They're going to give you all kinds of fits. Most. I'm saying most. There are some exceptions to the rule. Okay. Log, monologue, diatribe over. I like to lift the legs on these electrolytics and test them too while I'm here, because these things have a tendency to dry up and go bad, because these things were made 20 plus years ago. And this is a pristine example of it. It's a pristine example of Worthmore's handiwork and craftsmanship. Okay, let's get on with it. So here's our 2N222, our key-in transistor. We'll fire up our handy dandy little Atlas. And it's showing this guy's got a gain of 98. Not showing any real leakage or anything on this transistor. So the mystery deepens. I'm going to go ahead and I'm going to modify it. I'm going to put a new transistor in it, and then we're going to see what we get out of it for results. Because there's been a few rare times where the transistor tests good on the transistor checker, but then when you go to use it, it don't do shit. So we're going to go ahead and we're going to put the operate standby switch here, and then we're going to put the auxiliary keying circuit like right in here someplace for him. And then we'll button up the wires all real nice and neat in here, and then we'll go ahead and we'll put a brand new transistor in it, and then we're going to run it, and we're going to see what's going to happen. So when we come back, the switch will be in, the Tiffany RCA, that's a Tiffany. The Tiffany RCA jack will be in, and we'll have labels on the back. So give me just a minute, we'll get this banged out real fast. I thought I'd hop on here real quick before I went any further and give you guys a little update. So I got the manual key circuit installed, and that's working fine. I got the amplifier to key, it's not a big deal. The auto key circuit immediately blew this key-in transistor. And so then I went in and I tested this capacitor, which should be a capacitance value of 5, and it was reading 25. And then let's see which electrolytic it is. This one here is completely shorted out. So I just went in, I replaced the diodes, put a new cap in it and a new key-in transistor, and we're going to hook this up here in just a second and see if it works. Now, once I got the manual key circuit working, I thought, well, let's see what it does for power. So I go to run it up, and this resistor just started smoking immediately. And so that tells me something down chain is messed up. So there's something seriously imbalanced here. So either we've got a pill down, one of these two caps have gone bad, or something has catastrophically failed on the filter board. And I had a small heart attack. I got out my 12 volt Anderson clip, and I went to put this clip in, and I stopped just right about like this. I went, wait a minute. I took my hand and I pulled it away, and then I moved my hand and I went, wait a minute, the positive and negatives are backwards. I mean, they're clearly marked positive, negative, and then on the other side, negative, positive, right? So immediately I called the customer and said, hey man, I want you to check your Anderson clip in your truck. Is it backwards? He goes, oh no, I don't even have the Anderson clip in my truck. I said, bro, did you hook this amp up backwards? He goes, no, blah, blah, and he used words. So, I mean, before I was even able to get this far, I was like, whoa, what's going on here? So I flipped the legs around and actually locked them in place. What he claims has happened is he took the connector off, and he just put it on here for delivery, and he didn't pay attention to the way he had the plugs wired in. Which I believe him, because I hook it up, and everything else seems to be working fine. In the little cursory 1 or 2 times I've keyed this thing, I'm focused on just getting the key and the auto key circuit to work. Now that I think that we've got that going, I'm going to test that here in a second. Now we can go focus on what's going on. It wouldn't surprise me if this thing's got a pop pill in it, because it is acting like it's got a bad transistor in it for sure. But no, just put a manual key circuit in here. So just the RCA jack, put a little choke on it, a little disc capacitor to throw it out of resonance to make sure we're not bringing any RF in from the outside world through this lead. Made the red wire common bus, and that's what attaches to this lead over here on the bottom of the relay. Then I made the black wire, and it goes over and it attaches to the leg on the transistor. We don't want to have the transistor in line when you've got a manual key circuit. It'll blow the transistor up. So now I put the manual key on the bottom peg. So when the amplifier is sitting on its lid, up is manual and down is going to be auto, right? Okay. Let's go ahead and hook this up. And I spent a lot of time looking at these 10 ohm resistors or 15 ohm resistors that are in here. And some of them have got flux on them and they look a little rough. But this one looks discolored and a little brown. So we're going to put very low drive in it, just see if we can get the key in circuit to latch. And then we're going to come back around, we'll take a look at it and see what transistors are lighting up, one or not. And then we're going to go and see what caps are getting hot and what's not. Because it's only putting out about 200 watts of power right now. Give me a second, let me get the filter board all hooked back up, and we'll give it a test and we'll go from there. Okay, so we're on 80 meters, and we're going to put 1 watt into this thing. So manual is working. Auto. Got that fixed. It was easy peasy enough. I sit around and think about that for a second. I'm like, man, why doesn't the auto circuit on this thing work? I was like, what the hell? Okay, so let's come over here. As we can see, our balance resistor is smoking hot. Let's change what we're looking at. Thermal only. It's smoking hot. So that transistor's lighting up. That transistor's lighting up. That transistor's lighting up. This N transistor here is as cold as they get. Or its partner is making power. So this N transistor is popped. So it means it's got nothing to do with this filter board, nothing to do with these capacitors, because I've had both of these fail in the past. It's, brother, you got a pop pill. Well, let's pull this cap off and use the fans to bleed out the electrolytics. Let's pull this cap off and we'll pull this resistor out of the way, and we got to lift this ground bar up, and then we got to lift this ground bar up. So I've got to take this cap out, take the ground lead out, and peel back the solder wick that's over the top of that thing, and we'll get that transistor dug out of there, and we'll see what the deal is. I don't want to call it dead until we have it on the transistor checker, but I feel like no transistors. I mean, left the chat. So, okay, away we go. Okay, so first transistor out, and it tests at a 32. So whatever I put in there as a paired transistor has to have an HFE gain of at least 31 to 32. Let's let's pull this other guy out, and let's give it a whirl and see what's going on. If it tests good, that's great, right? And then we know it's something else, but I have pretty solid suspicion that something's awry here. So let's get the camera all set up. These darn Toshibas are getting so spendy anymore, it's ridiculous. But in the same breath, it's like I sell them at $150 used, right? But that's after I've located them, got them here, tested them, wrote numbers on them, straightened the legs out on them, cleaned them up, made them look pretty, and put a lot of work into them. And then I just laugh because I get on the internet and I see people selling theirs on Facebook or whatever, and they're trying to get $150 to $200 for them. And I'm like, you guys, it's not how this works, right? If you really want to sell a used transistor, you have to market it 75 or 80 bucks. That way people like me that actually have money will come along and invest money in the gamble of buying your used transistors to be able to put them into operation over here after we test them, clean them, and certify they're working, right? Just saying. That's why I read this. Man, only $150 a piece. It's great. Good for you. You can ask that if you want. I mean, it's not. I'm not going to buy them at that price. It's kind of like I'm in business to make money or something and provide for my family. Yeah, see, this transistor's popped. Let's clean the thermal jizz off my fingers here real quick. Let's make sure we got a good bite on the leads here. Whoop, see, like this here. Yeah, it's done. So, this good, this no good. Don't know why it happened. All I know is it happened. All right, let me get some Q-tips out. We're going to clean the transistor pockets out. We'll go ahead and we'll reinstall this one. I will find a match for this one in my pile of used parts. And this amp should be back up to full tilt, running just like a Swiss watch here in just a few minutes. Every one of these things is always a little bit of an adventure. Okay, so this is 16 volt 1000 UF electrolytic, and it's testing out at a 0.42 ohm. It's really good, less than a half ohm. And we're seeing 9,840 UF. I was debating if I needed to replace these. I think I kind of alluded to that in the previous segment. This is also a 16,000 volt, 16 volt 1000 UF cap. Analyzing 4.3 ohms, so it's within spec of this one. 9978. These are both well within spec, so I can put them back in the box. And as you can see, we've got the amp all assembled back together. So let's see what it does once we get these electrolytics in there, what little they do to the circuit. Still, we want to try and have that level of performance of professionalism where we're going to check out all the things and look at all the things and twist all the nipples and turn the porch lights on appropriately, right? Okay, so before I replace it, we're looking at this resistor right here. No heat. No heat. So if you can remember correctly, before we were putting 1 watt of carrier in it, which we're still doing, 1 watt, 75 out with 1 watt going in. And we're in balance. And we're on 80 meters. So, all right, let me button up a couple things, get the workbench cleaned up here a little bit and put some tools away. I mean, it wasn't that bad. All we had to do is change all these parts. I mean, every one of these is a little bit of adventure in their own. I want to replace this resistor before we go any further because, well, it is discolored, which means it's out of spec. I went ahead and I replaced the 15 ohmer that's back here, our little indication resistor, I mean, our base resistor. You guys know that's a joke, right? I literally had somebody say, man, what are pills? And what's 10 ohm smoke? It's like, well, okay, so you're new to the language. I'm explaining that to somebody the other day. You know, the amateur community guys, that's their own language. The CB guys, that's their own language. CW is its own internationally recognized language. Then you have tech, the actual legitimate technical terms for everything, which is its own language, right? How many languages do you know? I know at least 5. Oh, God, they used to give me shit in high school about being a dork, how it would never work out. Uh-huh. Okay, let's see if I can do this and not frickin' screw this up in any way here. Okay. 1,000, and these are... Okay, so let's break this down a little bit. So this is our RF coming in, and this is our RF going out. Okay, so how this works is because I had a guy on Facebook ask a question about how he couldn't find any materials on this anywhere on the internet. And I was like, what? And this was in my group. So then the post started coming. I'm like, dude, just literally type BBI amps and Worthmore into the internet and you'll get a phone book. But then I realized I've never like really broke down how the amp works. This relay is our primary transmit receive relay. This one here is what's controlling our bias circuit. But the output power loops through this relay as well. We're just using one pole of this. So first off, what happens is the RF comes in. It comes in on this lead, and that lead comes around and it goes to this relay, and here is your input and output power. This is your bias circuit. It is comprised of 2 33 ohm resistors, and then here's your load resistor here. So you feed this 12 volts switched, which is through this relay, or through this trace. Then it represents the load, which we can adjust with these 2 resistors here, a little filter cap, and this would be like a 103, 104 disc capacitor to help keep RF out of this circuit. That's a 104 and that's a 104. So you got a 104, 2 33 ohm resistors, which works out to be about 15 ohms. I personally like to use a 10 ohm resistor, a little 16 volt, probably about 100 UF filtering capacitor, and a standard 1000 volt 1 amp diode. That's all it takes. So then the output of this circuit drops on this trace, and it runs up here and it goes to the input transformers. The input transformers thus have 1,000 picofarad apiece on top. These are 104s and these are 100 ohm resistors, the harmonic suppressors. There's 5 wraps on the input, 5 wraps on the input, 5 wraps on the output, which gives us a nice flat response. The input network, our RF, comes through this wire here, off this relay, goes up, goes through, comes over to this attenuator network, which is about 10 dBs, I think, if memory serves me. That is a 20 picofarad, 20 picofarad, and a 15 picofarad capacitor. 100 ohm resistor, and then we've got brown, green, brown. Brown, green, brown, as we all know, works out to be 150 ohms. And then we've got red, black, brown, which is another 100 ohm resistor right here. So 20, 20, and 215. Then the output power of this comes directly from here and from over here on the trace. Runs around, it comes over to our 5-to-1 splitter, which costs us about 1 dB and a quarter of input signal. Just this whole circuit, just this trace and this here, we lose almost a full dB and a quarter with the input signal. I know this because I looked at it with a network analyzer in the past. Now, this is where we start breaking from tradition on most CB amps. Most CB amplifiers, we would grab up on this trace, preferably at the feed point or at the input network over here. We'd add all of our capacitance to ground. The tuning capacitors for this circuit are 20 picofarad, 20 picofarad, 500 volt poly constructed capacitors, one here and one here. Okay, our bias circuit continues on this trace, then there's another little ferrite bead, and then it feeds this transformer. There's once again a 104 here and a 104 here. that helps throw the circuit out of resonance, so RF doesn't want to feed back into the circuit. So then we have our 115 ohm or 150 ohm suppressors with 104s on them on our harmonic suppressor. And that's to help suppress the spurious RF emissions that can be created from an oversaturation point in the input transformer versus what the actual transistor can uptake in RF. That's all these do. This resistor, this one, and this one. We have two poly-based caps again. One's 1000, the other one's 160, or pardon me, 660. Off the side of each one of the transformers, we've got another 120 picofarad capacitor. So over here we have a 103 and a 104, and then we have another 16 volt 100 UF electrolytic, not UF, pardon me, UF electrolytic. The output again is 20 and 20. Remember, we're trying to create a flat response palette. Another 5-to-1 with a balancing resistor of 100 ohms, and this is also 5-to-1 up front on the input with another 100 ohms. Our output power comes out down this trace, jumps onto this wire, and just this joint right here costs us about a quarter dB worth of signal. This costs us another quarter dB worth of signal, and this costs us about a dB worth of signal. Just in the efficiency of it running, but there's no really better way to do this. The output RF from the palette goes to this side of the board. Okay? So as we select the different frequencies with our rotary switch in the front, this one does not have an auxiliary jack on the back or on the front. Some of the Worthmores did. And they just parry this switch. So you could flip the switch into auxiliary, and it would allow you to have the remote. 1, 2, 3, 4, 5, 6. So it's a 6-position rotary switch. Each position is dual, so we have a corresponding connection for over here for, let's say, 160, and then on the opposite side of the switch going out, we have a 12-volt source that runs the LEDs. So for all 6 positions, we have a 6-position, what they call dual pole switch. So it's single pole, dual throw. And as we move through our arc of motion, it's feeding 12 volts either thusly onto each LED, which is going through our standard 1K resistor to knock the voltage down to 3.5 or 1.5 volts. Because as we know, all LEDs are 1.5 or 3.5 volts unless it's previously stated otherwise on the packaging where they have an internal integrated resistor on the LED. International volt standard for LEDs. Okay. We drop 12 volts on the 160 meter filters here, and then 80, 40, 20, 15, and then 10. Very simple. I've done many videos on how to do these filter boards. Many, many, many. I think it would really behoove somebody out there in the land of creating things if they would make a multi-kilowatt filter board. I think the universe is starting to head us in that direction. The output RF comes back down. Now, just because of this connector, costs us another quarter of a dB. This connector costs us another quarter of a dB. The opened air non-balanced coax connection, or unbalanced coax connection, however you want to argue it, will cost us a little bit more signal. This entire filter circuit, each one of these banks, also costs us a little bit of signal. But the tune for each one of the frequencies on the output side are these capacitors. This one, this one, this one, this one, this one, and this one, depending on the band. Does that make sense? Okay. RF comes out, drops down, goes directly to our relay, and then comes out. The on-off switch, there's a positive 12-volt source, which is right here. Once again, a 103 or a 104 on the positive rail to help keep RF from getting onto it and saturating the electronics on the fan. And these are our fan pickups. Blue is our fan ground, and this one here is our positive switch. That's it. Very simple. What we updated here is, instead of using dual caps, I used one cap at the appropriate value. Put a brand new 2N222, another coupling diode, and then over here we put our coupling capacitor. Added a 103 here on the RCA jack for the Emmanuel function. Like I said, once the lid's on, switch down's auto, switch up is going to be manual. today we're going to operate in manual because we're going to be running everything on sideband with the ICOM 706 or 7300. So we're going to use our foot pedal, which when the amp is on, we're in auto, there's manual, just like so. I just lied to you. I literally have this labeled backwards because I'm half-baked retard most of the time. Jeez, I even looked at this. Oh, that's how it goes together. When the lid is on, down is manual, up is auto. All the instructions, because I got them backwards on the video, believe me, the labels will be on here appropriately now. So there's man relay, which stands for manual relay. This is auto relay. If you have one of these amps, do not use it until you either have a manual hookup or keep your drive level relatively low, otherwise you'll end up eventually burning off the contacts. Remember, these relays are being repurposed. This is a DC rated relay and we're putting an AC signal through it. Okay, let's go ahead and let's move on to the run portion of this video. We're going to use our spectrum analyzer. So over here we're set at 0. In the middle is 250 megahertz and at the end is 500 megahertz. We are running over here so that we don't absolutely launch my spectrum analyzer, blow the front end out of it. This is a 35 dB down attenuator, which is going in the opposite direction to the RF flow, which is fine. It still couples exactly the same. The RF goes up this dual 316 shielded coax, goes over to this splitter that hangs here on the wall. It in turn knocks the signal down again. So now we split this signal, and this is what runs the Hickok freak counter and deviation meter and mod meter. Then we come up here and we have the signal split yet again. This drops it down an additional 5 dBs each way. One goes over to the spectrum analyzer, the other one goes over to the oscilloscope. And from here I've got an additional HP attenuator. Currently got 15 dBs knocked down. Sorry, got 15 dBs knocked down here. That's how this all works. This never changes. I've done many videos on how this is all set up. So we're about 50 dBm down, and we're just trying to knock the voltage down to where it's in the microvolt range. Millions of volts. Millionths of a volt. So we're going to be doing all of our work within this little tiny bit of the scale. It's going to be down here. All the work that we're going to show. First couple bands, 160 and 80, are going to be down here. So we're going to be looking right at the edge of this to show our signal growth and where we're at, and then we're going to progress up through the bands. Is it going to be spot on? Don't know. Should it be? Yes, pretty much. Okay, now we got that all explained. And I made sure to turn the brightness way up because I did get a comment the other day. It's like, your video is too dim. I can't see what's going on. I was like, okay, well, turn the brightness up on your phone or whatever. He says that doesn't help. So we're going to overexpose this a little bit. It's not like I don't have a little window in my screen on the camera that shows me right here what my white balance saturation is. We're currently overexposed, by the way. That is a 1,000 watt slug-in peak. That is a 1,000 watt slug-in average. That is a 5 watt slug-in reverse back from the Bird 10,000 watt dummy load in millivolts, millionths of a volt. Cha-cha. Okay. So we're going to start on 160. I'm going to show you drive. Hello, 1, 2. I have the power on the ICOM 7300 turned to half. All right. Hello, 1, 2, 1, 2. About 11, 12 watts in the average mode. Peak mode. Thank you, Robert, for making that so easy for us to switch from peak to average. Hello. So I'm going to put about 40 watts in it in peak. And once again, our voltage, we're running at 12 volt flat, just like if you had it in your vehicle and the vehicle off. All right. Hello, 1, 2, 1, 2, 1, 2, 1, 2. Relatively clean. Hello, 1, 2, 1, 2. There we go. How the band selector works, by the way, let's cover that since I just shown it on video. Remember, not all RF that goes through this meter is useful RF. And I'm going to show you exactly what I mean here in just a minute. This is a low-pass filter, switchable low-pass filter network. It lets the lower frequencies pass, meanwhile it cuts the higher frequencies off. This is 160. So it is going to shunt or cut off all of the upper frequencies. As we go up in frequency, we're grabbing up, this is now a high pass or a low pass filter, so it's letting 80 and 160 through. And as we go up in frequency again, this is now going to, let's say, 40 meters. Now it's going to let 40, 80, and 160 through. And of course, the capacitance for the input tune change, or the output tune changes, which dramatically affects the way the amp's going to operate. But I want to show you something. So here we are on the 160 setting. Hello, 1, 2. Let's step on the pedal. Hello, 1, 2, 1, 2. We're getting 400 watts there. Now let's go look at the spectrum analyzer. Now I make the argument all the time, and I'm going to offer this up as proof. I make the argument all the time that amateur solid state boxes have the potential to be way worse at creating harmonics than 90% of CB amplifiers ever created. Now, I'm going to show you exactly what I mean. The palette is a flat response. We use the filter to make it so that it is clean. Hello, 1, 2, 1, 2. You guys can't even see it, can you? Hello, 1, 2. It's there. It's way over here. Because remember, we're like 1.8 megahertz. So now we're going to go here. Let's pan out just a little bit. I want to get as much of this in shot as I can. So, hello, 1, 2, 1, 2, 400 watts. Now we're on 12 volts, right? Now watch what happens when I take it all the way over to the auxiliary position, or we'll just say 10. Hello, 1, 2. Now, we're seeing 200 more watts out of it on the watt meter. 200 more whole watts, right? Guess what? That's 200 watts of non-usable junk. Remember how it was nice and clean and we couldn't even see the signal all the way down there on the end of the scale? Hello, 1, 2, 1, 2. All of this garbage that we're seeing here is stuff that's going out as spurious emissions that no one is going to be able to receive because the palette is so wide and so diverse in frequency. The ham solid-state amplifiers can be much dirtier than 90% of the hyper monoband 11-meter boards. So just keep that in mind if you're an amateur operator and you're seeing this. And the next time you hear somebody say, well, I'm damn CB splatter boxes. That actually, come to find out, is not the case. Now the radio feeding the amplifier might produce a whole lot more worth of harmonics, but it's not the amplifier. I hate the term splatterbox because it's not the case. Us, people that work on some CB stuff, really pride ourselves on how clean we can make the CB monoband amplifier that has a very tight tuned response. So over here is 0 and over here is, let's say, 30 megahertz. We want 100% of that energy to go out on 30 megahertz so that we can have the most dominance on one frequency. This palette is designed so that, let's say, this is 0 and this is 30 megahertz, that it produces roughly the same amount of power on all frequencies. But when we do that, it now becomes because the operation of the circuit leans itself to being more capable of creating harmonics. And then we have to use a low-pass switchable band filter that'll allow us to work around that. Okay, so we're going to put that back on 160. Now let's show you what happens when we jack the volts up. So, hello, 1, 2, 400 watts. And remember, this is the drive power on the ICOM 7300 at half. Let's go down here. We're going to turn this to 14.8. Just like what would come out of your car. Take this over to peak. Hello, 1, 2. About 50 watts worth of drive. But now we're going to see a huge difference in the response out of the transistors from the increased voltage. Ready? Hello, 1, 2, 1, 2. So now we're getting our 600 watts out of this with 50 watts of drive. Hello, 1, 2, 1, 2. We'll take this over to peak again. Hello. 2 meters are reading relatively close. Now, let's go look at the spectrum analyzer. When we saw 600 watts before, it was all over the place. It was super dirty, right? Hello, 1, 2, 1, 2. Hello. My friend Gary, who is a rocket scientist, literally worked for Lockheed, and we were having an in-depth conversation about what do filter boards actually do. And this is 15 years ago, before we lost him to fibrosis and lungs. That guy was brilliant. I mean, he was in the top 5 smartest people I've ever met in my life. And he was approaching the conversation as an engineer, and me being a not know anything about anything, and I still don't know shit about shit. We were having a conversation about what this actually does. And the best way I've ever heard anybody describe what a filter board actually does, it's a heat generator. There's going to be some electronic experts that heard me say that, and they're going to friggin' melt down. Hear me out. They're going to melt down, their eyeballs are going to pop out, and their third testicle is finally going to emerge from their taint. All this does is generate heat. That's the end result. Remember, we must always conserve energy at all times, right? So if it's not something that we can relatively use on frequency, the energy has to go and turn into something, and 9 times out of 10 it moves to a higher state, which is going to be what? Heat. It's blocking the harmonics, that's for sure. But in the same breath, this is having to absorb the watts that are off frequency, and it turns them into heat. So I like to look at these as heat generators, period. It's the only way we can make this circuit operate, though, to where it's relatively clean, is with this. So now, let's go ahead and let's play the other card here. Let's take and let's turn the power up on the radio to 100%. Let's jump back a little bit in this lesson. And remember the harmonic suppressors that I was talking about? I call them flybacks. That's how I initially heard them referred to, but they do suppress harmonics. If you oversaturate the input of these transistors, there's no place for the RF to go. So then we end up having another heating issue that takes place with the input voltage bouncing back and forth, and it causes all kinds of weird problems. By us adding this resistor here, the 5 watts worth of dissipation, you can get away with using 2 watts in this position in the CB world. In the amateur world, we don't see that happen very often. In the amateur world, it's going to be either 5 watt, or in Ameritron's case, it's 3 watt resistors. We need to dissipate the oversaturation of RF. Then we don't have a rise in the tune and the input circuit from the differentiation of voltage bouncing back and forth. That's all SWR is voltage that's not resonant for whatever circuit, and it's going ping pong, ping pong, ping pong, ping pong, ping, until it eventually dissipates itself. Remember, we've got to conserve energy at all times, so therefore it just moves to a state of heat. And it'll usually stack the heat up on the weakest link of the chain, which is either going to be a trace, or it's going to be the contact point in the relay. That's why guys with high SWRs, they'll burn the relays out in their amplifiers. And they don't understand that that's what's causing the problem. It'll just ping pong back and forth, or it'll find some random connector in the chain of events from here to the antenna, and that voltage will just stack up on that highest point of resistance, and it'll make it hot, and it'll dissipate. Its SWR gets dissipated in heat, and that's what causes the connection to blow up. Okay, so now we're going to move into the land of putting about 100 watts into this amplifier, which is not, I mean, that's slightly abusive to this. To the 8 transistor version of the same amplifier, it's not. To this is just a little bit much, but we'll be okay for video's sake. Hello, 1, 2. So now we're seeing 30 average. And hello, about 100 watts peak. I get asked this about once a week. Why do I still use the analog meter? Believe it or not, there's a lot of people that watch this channel. It's diverse. Okay, there's a lot of people that are very used to looking at the analog meter and they become confused when they look at this. There is another large group of people that look at the digital meter and it instantly clicks for them. So in my attempt to try and pander to all audiences, that's the reason why we show the reflect to the dummy load. We show it in average power, even though don't even get me started on that. And then we show it on peak on this meter, and I try not to move the elements around that much because it gets everybody confused. Okay, with the 100 watts worth of drive, hello, audio, hello, audio. We're not seeing any increase in output power here. We're still about 610 watts. We were at about 600 watts with 50 watts of drive. Hello. So we're seeing 42 more watts with about 50 more watts worth of drive. That will change as we go up in frequency. Put that back in average. If you watch this video and you don't understand how the Worthmore amplifier works now, got a question or anything, you can call me and I'll talk you through it. This same circuit is almost universal when it comes to like the Henry SS750, the Metron, the Henry 1200, the Henry 2800, which is the most rare of them all. I've got one sitting over here I got to get through. The Worthmore 6, Worthmore 8, the SEC amplifiers, they're all the same. They're all based off the same principles. This all comes from the Motorola RF Engineering Hand Guide. That's how the guys that built the transistor designed the amplifiers to work around it. It's all the same. The ALS 500, they're all the same. They're the same. They are the same. The parts might be in a different place. The attenuator might be a little bit different value. There's different capacitances that people have applied based on transformer size, trace size, and that kind of thing, but they all basically work on the same set of principles. Okay, let's go ahead and let's go to 80 real quick. And let's make sure we got good clean operation on 80. Hello, 1, 2. Now we're seeing a difference. Hello, 1, 2. Now we're seeing a lot of difference in output operation. Remember how I told you that would change? Hello, 1, 2, 1, 2. Let's go over here to peak mode now. Hello, 1, 2, 1, 2. Okay. Look at this. Hello, 1, 2, 1, 2, 1, 2. I don't like having my spectrum analyzer set up so wide. I wish I could have that a little bit narrower, but I've had many people request that I show them way up in multiple integers of frequency. Me personally, I wish I didn't have to have this set so wide, but the so-called everything, I've been to school and been educated on everything, real RF technicians, whatever, they want to see, all they care about is the upper integers and frequency, where me personally, I want to be able to zoom this in knowing that we're not going to see anything in the third and the fourth octave, and I want to see what's going on down lower. Because what if my buddy's transmitting on, let's say, 80 meters, I can't see what's actually showing up in the second resonant octave going the other direction in the lower end of the band. What might be happening on 160 or below. So we're just going to stick with it for now. Let's see, I can't remember what the next band is here. It's, oh, look at that, 40, imagine that. Okay, let's go over here to 40 meters on the radio. Guess I need to actually start showing the front end of the radio. 11111, that's going through the amplifier. Let's establish drive. Hello, 111111, hello, 11. Okay. This is in peak mode, by the way. Hello, 1, 2, 1, 2. This So this is at 14.8 volts with 100 watts worth of drive. That is a lot to ask out of this amplifier on sideband in normal operation. All right. If we look at it in the average scale, hello, 1, 2, 1, 2, right around 500 watts. But oh my God, that much power out of 4 transistors? You're oversaturating the transistors and it's going to be a splatter amplifier and you don't know what you're doing. Ha 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 ha, keyboard warrior. Literally can see the guy in camo gear and he's got the keyboard thrown over his shoulder. I argue the other direction because, well, I have proof. Hello, 1, 2, 1, 2, 1, 2. And as you can clearly see, we have no second, third, or fourth order harmonics at all. I would probably say 98% to 99% worth of the power is going out on frequency. Hello, 1, 2, 1, 2. Well, those have to be ghost watts because the input SWR is so high that it's false power. Hello, 1, 2, 1, 2. I don't think so. I argue the other way. I really do. Hello, 1, 2, 1, 2. It's a 5-watt element reading in reverse. And it's sitting between this radio and this radio. Or sitting between, this is sitting between here and the amplifier. So we're seeing just a little bit less than a half a watt worth of reflected power coming back. I like Worthmore's. Worthmore was a rebel. I don't think he quite understood what could happen if he would have gone and gotten himself a type acceptance piece of paperwork. Because this little amplifier, and they have consistently outperformed anything that is commercially made. He could have made a killing if he would have filled out the paperwork and paid the fees to the FCC to get a type acceptance sticker for this piece of equipment. I've repaired, I don't know how many of these. I've owned several of these. I repaired his own personal amplifier that he had. It showed up here on this workbench. They ran it, the ham community come down on this guy like a loaded stack of bricks. Like he was committing apostled Christ crimes, right? And drug him up on the cross, stabbed him in the side, and then laughed at him after the fact. None of them bothered to look at what he was actually producing. Now, I never met the man. I didn't know his personality. I know nothing about him other than looking at what his craftsmanship put into the radio community. All right, 14 megahertz, let's go. Radio, 111111. Back down here. Hello, 111111. Peak numbers. Hello, 1111. Hello, 11111111. Now we're going to start watching our power drop off. I've explained this in many videos. Because this board design is designed to be flat in its response, and we're using this filter board as our output tune for frequency, we'll say this is 0 megahertz, so 0 megahertz, and over here again is 30 megahertz. The response curve of this network looks a lot like this. We have to admit that a majority of work that takes place in the amateur HF bands, in the lower portion of the bands, 80, 40, and 20 is where most of that work takes place. Most of the Worthmores I have seen, and 80, 40, and 20 are right about here in the middle of the band. Actually, 20 is like right here in the middle. 14 megahertz. This is 30. This is 0. So the frequency response looks like this. So 160 was 600 watts. Then 80 was 1,000 or 800 watts, right? And then 40 was 1,000. Now we're at 20, so we're starting to be on that downhill side of things. So 20 megahertz at 14, 20, 20 meters at 14 megahertz is going to be right roughly in the middle, right? So we're going to see that trace just continue to go. Okay, so I think the next step on the Worthmore is 15, if I'm not mistaken. Yes, 15. Which translates to this band here. Let's go to 21. 1, 2, 1, 2, 1, 2. Hello, 1, 2, 1, 2. Starting to drop off. And now let's go to 10 meters. 29 megahertz, dead on the money. Hello, 1, 2, 1, 2. And hello, 1, 2, 1, 2, 1, 2. But we're telling you, BBI, that it's a splatter box because you're using it on 10. No, it's not the case. This amplifier would have easily passed an FCC inspection. Hello, 1, 2, 1, 2. That's our drive input power. Hello, 1, 2, 1, 2. We could tweak this a little bit and get this second order harmonic out, but you got to remember we measure how far down it is from our principal, which is at 0. Hello. That little second order harmonic is just what? 3 dBs, 4 dBs worth of noise. You could change one cap on this and get rid of that. Or we could try and squish the coils together or separate them out to increase or decrease our unihenry response to the circuit, otherwise affecting its broad spectrum. I don't care what anybody says, these are good looking boxes, and this one is in great shape. Came in here not working. Oh yeah, auto. Let's try the auto key. Let's go ahead and we'll disconnect the manual key. I'll get this out of the way. The problem with running this on manual on sideband is that there is no relay delay, which isn't, that's a CB term, by the way. There's no capacitor that couples with the keying transistor that senses the incoming RF that holds the relay open. So when you use this amplifier on sideband, the relay in between each one of your words is going open, closed, open, closed, open, closed. As we discussed earlier, there's an initial arc that takes place with the relay moving, with the RF being live on the relay. We have just now exponentially increased that arcing process by only having an auto relay. Hello, 1, 2, 1, 2, 1, 2, 1, 2. Listen to the relay. Hello, 1, 2, 1, 2, 1, 2, 1, 2, audio. Every time there's a little arc that's drawn on the relay, I can't look at this overexposed whiteness, dude. You're gonna have to turn the brightness up on your tablet. I'm not doing that in every video. I'm forcing everybody else to deal with it. Every time that relay draws an arc, for a nanosecond, there's a dead short because the RF has nowhere to go, either coming in the amplifier or going out of the amplifier. The armature that attaches to the outside world is in transit between the pole contacts on the relay. And then we have another thing called relay lash, where the armature that's moving, the little paddles, they'll slap, but they bounce. So it's contact, 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 and contact, contact, contact. And every time they bounce, the conductivity, but it happens fast. So what we see is, what's really happening is, just saying. Well, my man, this is supposed to be like a 5-minute repair, and it ended up being a 1.5-day long saga because of myself, Mr. Scott. You're done. It's upgraded. The other thing I could do is I could add another switch for SSB control and put a capacitor on here, but I don't want to. Scott, you must buy for your ICOM 706 Mark II-G the auxiliary jack with the RCA plug on it if you want to run this in your truck. And you also need to acquire yourself a very good legal limit antenna tuner, because this thing we have seen, depending on his drive, can do up to 1,000 watts. Peak power, right? Food for thought. Gentlemen, my name is BBI. Without a shadow of a doubt, I'm the biggest mud duck, period, in Idaho. Period. By like a lot. But that sounds arrogant and foolhardy to say that out loud. I'm a repair shop that is grateful and is humble that I get to work on all of these projects, and I appreciate everybody recognizing I'm a one-man band and I do everything myself. The video editing, the shipping, the receiving, the phone calls, all the parts ordering, everything. And even at that, people are patient enough to let me work on their equipment, and I am humbly grateful for that. I've created a lot of mini-me's, and I'm proud of that too. There's more work than what one guy can do. And I've created quite a few people now that are starting to fill the gap. And the phone isn't ringing as much, which is good, because now they're calling all these other people. And that's great. I support the whole hobby, not just my pocketbook. Super shout out to the guys here on Patreon. They're the ones that allow me to spend most of my day on the phone. They're the ones that allow me to be able to buy all the fancy video equipment and camera equipment and pay for the memberships that I have to pay and the subscriptions I have to pay for the video equipment and the editing, and allow me to have an update computer. If you have ever learned anything from my channel and you want to show your support in any way, please come join the guys here on Patreon. And they're the reason that we've been able to sit here for about an hour now with each other together and talk without any commercial interruption from YouTube. Yes, I understand there's a thing called ad blocker. I know all about it. Yes, I understand that you can pay for yet another subscription platform through YouTube and you're not going to see any ads. I understand all about that too. But there's a lot of guys in our hobby that don't want to pay for yet another subscription. They don't want to figure out ad blocking. I want to provide them content so that they can watch it on their phone and not be harassed by the adult diaper ads, the Liberty Mutual car insurance ads, the State Farm car insurance ads, and on 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 and on. I want you guys to sit down and be able to enjoy the content. And because these guys here on Patreon provide monthly support to help me compensate for that, I say thank you to them, and I hold them in the highest esteem. Super shout out to Penta Labs, Excess Power, Siglant, Odyssey, MechMan. Yeah. These guys have been instrumental in making this channel go. Big shout out to Steam and Coax, Bird, and Coaxial Dynamics, of course, over here. I had a fan, supporter, gentleman come through here the other day, and he sent me these. Just like the old-time electric signs that used to be wrapped around power poles everywhere. Kids, don't play with the high voltage, it'll kill you. The other thing he sent up here is he's been watching my channel for a long time. And I've been waiting to have the right opportunity to measure this out. I said on video one time, when I was working on a 24-pill board, that the amount of copper that is hammered out and then dissolved and then reattached to the phenolic was about that of a dissolved penny. In this little pouch, this is a coin pouch, and I got to be very careful with this, that gentleman took a 1-cent penny and dissolved all the metal out of it except for the copper. Same guy that gave me the Johnny sign. And I have it sitting like that because I have memories of every sign I've ever seen in real life that was the same sign. In real life, hanging someplace, was only usually held on by one nail and was a little bit rusty. It's hanging that way for a reason. I want to eventually take and scrape an entire 24-pill board up and measure the total amount of copper weight and back it up against this. I think I'm off a little bit now that I've seen how much actual copper's in a penny, which this thing does. This, you can barely feel that it's in that plastic. There might be 2 pennies worth of weight, but that's a video for another day. Gentlemen, I want to say thank you to all of you. Thank you for following along. Hopefully this helps somebody and answers some questions. Like I said, I know this amplifier like the back of my hand, right? If you're running into a problem and you don't know, come hit me up. On that note, I'll see you guys. I appreciate every single one of you. Click, click.